Alright, so section 9.2 deals with graphing simple rational functions. Now, when you graph a simple rational function, the graph is going to be a hyperbola. A hyperbola has two symmetrical parts called branches, and the branches are always diagonally opposite each other. So if you want to think about what that looks like, if I'm going through and I'm graphing, we're going to, on our coordinate plane, we're going to be identifying two asymptotes. So let's say our asymptotes are here and here. So I'd have a vertical asymptote and a horizontal asymptote. And then I'm going to have two branches, and the branches come in along one asymptote, pass through several points, and go out through the other asymptote. They're always diagonally opposite each other. So if I've got one branch up here in the upper right, the other branch will be down here in the lower left. And they are also symmetrical, but these are inversely symmetrical. So if you remember when we graphed points on one side or the other of the vertical axis of symmetry in a quadratic function, then we were able to match to points on the other side of the axis of symmetry, and they were directly symmetrical. So I would do on the right side whatever I had done on the left side. In this case, they're inversely symmetrical, so whatever I do on the right side of the vertical asymptote, I'm going to do the opposite on the left side of the vertical asymptote. And they are symmetrical, inversely symmetrical, around the intersecting point of the two asymptotes, which is the center of your graph. Okay, so that's an overview of what graphing a simple rational function is all about. But we haven't really talked about what is a rational function. Well, a rational function is a function that will fit this model for a simple rational function. And the rational function is basically a function that has a function in the numerator of a fraction and another function in the denominator of a fraction. Okay? There are two different types of simple rational functions that we're going to be working on. Pardon me. So one form of a simple rational function has a base equation of y is equal to a divided by x minus h plus k. So again, we have our h and our k, and the key thing in this is that we're going to identify h and k, and we're going to use them to identify our asymptotes. Okay, you will notice also that in this form of the function, in the numerator, we have just a constant number. So you see a is in the numerator of this function. If you look at the other form of the function, you'll see that what we've got is we've got a linear function, or some function that involves our variable. And in the case of simple rational functions, we never have a function as our numerator or our denominator that is a degree greater than 1. So they're all going to be linear functions. Okay, that's what makes it a simple rational function as opposed to a general rational function. What differs in these two types of functions is how I identify the asymptotes. Okay, so in this case, I would find one asymptote, which would be the vertical asymptote, by setting the denominator to be equal to 0. So if I just take whatever's in the denominators, in this case cx plus d, and I set it to be equal to 0 and solve for x, the resulting equation would be my vertical asymptote. And my horizontal asymptote will always be the leading coefficient in the numerator divided by the leading coefficient in the denominator. And that y is equal to a divided by c will be my horizontal asymptote. All right, so let's go about graphing simple rational functions. So the first thing I want to do is I want to identify my asymptotes. So you can see here I want to find h and k, as we've been doing all year long. So h in this case is 3 and k is 2. So I know I'm going to have asymptotes that are x is equal to 3 and y is equal to 2. Okay, after that I'm going to do an input-output table on one side or the other, either to the right or the left of the vertical asymptote. Okay, but right now we're just going to work on identifying asymptotes. So if we look at this equation, right, this is in the different form, ax plus b over cx plus d, and I want to set the denominator to be equal to 0. That's how I find my vertical asymptote. So 3x plus 1 equals 0. And when I solve for x, 3x is equal to negative 1. So x would be equal to negative 1/3. So that's one of my asymptotes. And my other asymptote will be the leading coefficient in the numerator, that's 2, divided by the leading coefficient in the denominator, that's 3. This is my other asymptote. Okay, so that's just how you find the asymptotes as you're graphing these functions. So let's go ahead and graph a function. So remember that my asymptotes here were x is equal to 3 and y is equal to 2. So if I go through now and I put those asymptotes in, here x is equal to 1, 2, 3, vertical line through 3, and y is equal to 2, horizontal line through 2. And now I've got this new, sort of almost like a new coordinate plane with a center here at 3, 2. Now my points are going to be inversely symmetrical from this point, not from the origin, but from this point, the intersecting point of the two asymptotes. That's the center of my graph. So I can do an input-output table to the right or to the left of this. Again, you should always pick the values for inputs that are the easiest that you can think of. So I'm going to pick 2, 1, and 0. I want to pick 3 points, and I'm going to work to the left of the vertical asymptote. So when I plug 2 into this equation, I'll get 4 divided by 2 minus 3 plus 2. Well, 2 minus 3 is negative 1. 4 divided by negative 1 is negative 4. And negative 4 plus 2 is negative 2. When I do the same thing with 1, I'll have 4 over 1 minus 3 plus 2. Well, 1 minus 3 is negative 2. 4 divided by negative 2 is negative 2. And negative 2 plus 2 is 0. And when x is 0, I'll have 4 over 0 minus 3 plus 2. This is going to be negative 4/3. That's plus 2. So negative 4/3 plus 2. 2 would be 6/3. So negative 4/3 plus 6/3 is 2/3. And if I go through now and I plot these points, I'd be at 2/3. I'll be at 1, 0. And I'll be at 2, negative 2. So my branch over here comes along one asymptote, passes through my 3 points, and goes out in a very shaky fashion along the other asymptote. Okay, now, I don't have to do an input-output table for the other side of this graph. What I'm going to do is I'm going to match the points using symmetry. So if from the center of my graph, the intersecting point of my two asymptotes, if I go 1 to the left and down 1, 2, 3, 4, that means I can go 1 to the right and go up 1, 2, 3, 4. So I do the opposite thing on the right that I did on the left. My next point was 2 to the left and down 2, so I'm going to go 2 to the right and up 2. And I went 3 to the left and down 1 1/3. I'm going to go 3 to the right. I'm going to go up 1 1/3. And now I've got the other 3 points. Come in along the asymptote, pass through the 3 points, go out along the other asymptote. And that's graphing a simple rational function. Okay, I've got 2 branches. They're diagonally opposite from each other, and they are inversely symmetrical. So I start off by identifying the asymptotes. Then I do an input-output table on either to the right or to the left of the vertical asymptote. And once I've done that, then I match points to the other side using the inverse symmetry. Okay, if I'm working in the other form, the steps are the same. The only thing that really changes is how I find the asymptotes. So if you remember, we set the denominator to be equal to 0, 3x plus 1 equals 0, and I was able to find that x would be equal to negative 1/3. And then for the horizontal asymptote, y is equal to the leading coefficient in the numerator, that's 2, divided by the leading coefficient in the denominator, that's 3. So y is equal to 2/3. In this case, I'm going to go ahead and do my graph in thirds to make it easier to show you the asymptotes. Okay, and when I put my asymptotes in, x is -1/3, that would be here. Y is 2/3, that would be here. And so my center here of my graph is going to be at -1/3, 2/3. Now I need to do an input-output table. Now again, we want to pick whatever values we feel are, let's see, 1, 2, 3, 1/3, 2/3, 3/3. Okay? 1/3, 2/3, 3/3. We want to pick whatever values we think are going to be easiest for our input-output table. So I'm going to pick 0, 1, and 2 because I think those are going to be the easiest for me to plug in. Now you'll notice also, because the variable occurs twice, I have to plug these values in 2 places in this function. So I'll have 0 plus 2 is 2, 0 plus 1 is 1. This is going to be 2. When I plug 1 into this, I'll have 2 plus 2 over 3 plus 1. Well, this is 4 divided by 4, which is 1. And in this case, when I have 2 plugged in, I have 4 plus 2 over 6 plus 1, and this becomes 6/7. Okay, so when I plot these points, I'll go to 0. Let's see, that's 1, 2. When I'm at 1, I'd be at 1, which is right about here. And when I'm at 2, I'd be at 6/7, which is a little bit less than 1. So I come in along the asymptote, pass through my 3 points, go out along the other asymptote. Okay, now I want to look at what I did in terms of moving from the center of my graph, the intersecting point of my 2 asymptotes. I went 1/3 to the right, and then I went up 1 and 1/3. So I go 1/3 to the left, and I go down 1/3, and then another 1 and 1/3, right? So there's 1 and 1/3. If I went 1 and 1/3 to the right, I went up 1/3, so I go 1 and 1/3 to the left, and I go down 1/3. I went 2 and 1/3 to the right, and I went up by, in this case we were at 6/7, so a little less than 1. That's a little more complicated to put in. But I'm going to go ahead and go over another 1 from here, and I'm going to put in my last point. Okay, so we go through the 3 points, out along the asymptote. And that's how you graph this simple rational function. Okay, let's do another example. The key here is I want to look at this problem and figure out which form am I in. Well, I don't have any x's in the numerator, so I know that this is y is equal to a over x minus h plus k. And I want to find h and k. Well, in this case, h is equal to -2 and k is equal to -6. So my asymptotes are at x is equal to -2 and y is equal to -6. So these are my asymptotes. And I want to go ahead and put those onto my graph. So x is -2, that's right here. Y is -6, so 1, 2, 3, 4, 5, 6. That missed a little bit. Let me put it back online there. And now I want to do an input-output table to the right or to the left of this vertical asymptote. So I'm going to do -1, 0, and 1 because I think those are going to be easiest. It doesn't really make any difference which values you pick. So when I plug -1 into this equation, this is going to be 6 over -1 plus 2 minus 6. Well, -1 plus 2 is 1. 6 divided by 1 is 6. 6 minus 6 is 0. When I plug 0 in here, I'll have 6 divided by 2 minus 6. Well, 6 divided by 2 is 3. 3 minus 6 is -3. And when this is 1, I'll have 6 divided by 1 plus 2 minus 6. So 1 plus 2 is 3. 6 divided by 3 is 2. 2 minus 6 is negative 4. So at negative 1, I would be at 0. At 0, I was at negative 3. 1, 2, 3. And at 1, I was at negative 4, right there. So I come in along this asymptote, pass through my 3 points, go out along the other asymptote. I want to match to the other side. If I went to the right one and I went up 6, I go to the left one and I go down 1, 2, 3, 4, 5, 6. I went to the right 2 and up 3. I go to the left 1, 2 and down 3. And I went to the right 1, 2, 3 and up 2. I go to the left 1, 2, 3 and down 2. Come in along the asymptote, pass through the 3 points, go out along the other asymptote. And there you go. So identify the asymptotes, do an input-output table to the right or left of the vertical asymptote, and then match your points to the other side using inverse symmetry. Okay, one more example in the other form. Now, this looks maybe like it would be the form we just did, but you'll notice there's an x in the numerator, so this is ax plus b over cx plus d. So to find my vertical asymptote, I'm going to take the denominator and set it to be equal to 0. So negative x minus 15 equals 0. If I add x to either side, negative 15 is equal to x. That's one asymptote. And to find the horizontal asymptote, y is equal to the leading coefficient in the numerator, that's 7, divided by the leading coefficient in the denominator, that's negative 1, so it's equal to negative 7. Okay, if I want to plot those asymptotes, I'm going to have to add some points into my graph. At x is negative 15, that's way the heck over here. Right, 1, 2, 3, 4, 5. Sorry, this is going to be a little bit of a mess. My asymptote's going to be all the way out here, negative 15. And my horizontal asymptote's going to be at negative 7. One, two, three. 1, 2, 3, 4, 5, 6, 7. All the way out there. So clearly I've picked a terrible example, and all of my graphing is now going to go right through my writing. So it doesn't really matter that I've picked a rather terrible problem. The process remains the same. You would still pick inputs to the right or the left of the vertical asymptote. So in this case, we'd be picking probably negative 14, negative 13, and negative 12, plugging them into our equation, getting inputs and outputs, and then going ahead and continuing with the problem. So I'm not going to finish this one out. You get the basic idea. The key is follow those steps. So you're going to identify your asymptotes, do an input-output table to the right or to the left of the vertical asymptote, plot those points, and then match those points to the other side using inverse symmetry. So go ahead and do your homework for 9.1, 9.2. I'll see you next class, and good luck.